Okay, so now we're going to look at finding particular solutions to these differential equations. So this means that we're finding the C. So here's our first example. We've got the differential equation dy by dx equals xy over x squared plus 1, and we're going to find the equation of the solution to the curve which passes through 1, 2. So you know when you do the integration you'll end up with a plus c part. Well, knowing that the curve goes through 1, 2 means we can find the particular solution out of that family of possible solutions and find out what the constant needs to be able to go through that point 1, 2. So we do separating the variables on this one. So we need to bring our y over to the left hand side, integrate both sides, and it looks like this. So 1 over y becomes log y. And x over x squared plus 1, well, the top is a multiple of the derivative of the bottom, so that's also a log. In this case it's half log of x squared plus 1, because if you differentiate the x squared plus 1 you'll get 2x. We just want the x on the top, so we need to half that, so we don't get that coefficient of 2. Now we know that when x is 1, y is 2, because it passes through the point 1, 2. So we substitute that in and we can work out what c should be. So log 2 is equal to half log 2 plus c. This tells us that c is equal to half log 2. So put it into our equation for the curve and we get this. Now this isn't its most tidiest form, so we'll see if we can just sort this out a little bit, especially because we've got those logs there. We can probably tidy this up quite a lot. So the x squared plus 1 and the 2, we can take out the coefficient of a half from both of those logs on the right hand side, and then adding together two logs means that we can multiply them. So that x squared plus 1 gets multiplied by the 2, and then we can put that half inside the log as a power. So that to the power of a half is the same as saying a square root. So remember, this was log y is equal to this. So then if we remove the logs from both sides, then we get y is equal to the square root of 2 brackets x squared plus 1. And just note at this point it's not plus or minus the square root, because we can check whether it should be a plus or minus by the point that we were given. So if you put in 1 and 2 into this equation here, you know that it only works if you take the positive square root. There may be instances where it would only work for the negative square root depending on the solution that you're being asked to look for, so you just need to check that if you're doing a square root one. Okay, next example. Show that sine y is equal to x is a solution of the differential equation, that one there, as follows, given that y equals 0 when x equals 0. Now this one is taken from page 220 of your yellow textbook, which is done in a slightly different way if you want to see two ways to do this equation. So x is equal to sine y, which means that if we take the square root of 1 minus x squared, that part out of the differential equation, that's the same as saying it's the square root of 1 minus sine squared y. Now that you should recognise as being useful from trig identities, so that is equal to cos y, since cos squared plus sine squared equals 1. So then if we take our dy by dx, we can substitute that in, so the bottom of that equation is equal to cos y. So then separating variables and integrating both sides gets us sine y is equal to x plus c. Now since x equals 0 and y equals 0, we can then show the following, that c is 0, so therefore sine y equals x we've validated as our solution.